Tomoyuki Arakawa from RIMS, who will be speaking about Hilbert Schemes of points in C2 and quasi-Lie vertex superalgebras.
I'd like to thank the organizer for this one. So I'd like to talk about some recent work with Toshiro. I'd like to start with explaining my background or motivation. So motivation comes from physics called 4D duality. So this was discovered by a group of physicists quite rather recently. So what they did was they defined some map or functor. So this part will be not rigorous because it's physics. Map from four-dimensional n equals to 2 superconformal field theories, whatever it is, the category of vertex operators, which you can identify with the category of 2D hierarchy, formal field theories. So this map was originally designed to do the following. So there is an important invariance. So this has several important mathematical invariants. One of the invariants is a numerical invariant called Q index, which is a certain Q series. And so the statement is that this Q series can be recovered from this image of this vertex algebra, which is in particular a graded vector space. So you can take certain, you can consider corresponding character. So this is defined by something like this, with some normalization factor. And the statement is that this map commutes. So you can compute this important Q series of the 4D theory, which is not mathematically defined, from the vertex operator algebra, which is something mathematically well defined. Okay, and there's some property of this map. The first property is this about this some constant C. This is called central charge, which takes positive value for unitary theory. And the statement is that the central charge is related with central charge for 4D theory. So there's a central charge for 4D theory by this formula. So minus 12 of central charge of 4D theory. So which means the physical theory is always unitary. If you start with unitary theory, you end up with non-unitary theory. It's a minus sign. So this means this map, this image is never unitary. So which in particular means that this is not surjective. Because a vertex operator, which comes from pure CFT, is always unitary. But if you start with 4D theory, you end up with a non-unitary theory, which is a bit exotic. But what is surprising is the so nanophysicists conjecture the following. So this map reduces dimension of quantum field theory by 2. So you may think it's natural to think this loses a lot of information for this theory, but in fact, this map is supposed to be injective. In other words, the vertex operator algebra corresponding obtained from this by this map is a complete invariant for this theory. So this is a great news because there's no satisfactory definition for quantum field theory of dimension higher than 2. But so this vertex operator algebra is something rigorously defined. So you can hope to come back from vertex operator algebra to this mysterious, interesting 4D theory. And if this is true, then it should, so as I said, this has several important invariants such as Higgs branch and Coulomb branch. And these things should be recovered from this vertex operator algebra. And the statement is that the Higgs branch of the 4D theory, which is certain hyperkiller cone, can be recovered from this vertex operator algebra as its associated variety, which is a spectrum of certain ring. So this is X is the associated variety of vertex operator algebra. Where V is certain Poisson algebra. V and it's called defined by the C2 algebra. I will not define this, so it's not so difficult to define this Poisson algebra, but if you don't know vertex operator algebra, it doesn't appeal to you at all, so I just try to explain in example later. So anyway, the statement is that this interesting hyperkiller cone should be recovered from this purely algebraic object, which is a vertex operator algebra. I'd like to make some comment on this conjecture. So first of all, the associated variety is in general just a Poisson variety. It's just a spectrum of Poisson algebra. In general. So vertex operator algebra coming from 4D theory has special property that just associated variety has hyperkiller structure. And second, the Higgs branch of 4D, so this is a Higgs branch of 4D theory, but you can do some procedure called S1 reduction to get a Higgs branch for 3D theory, where you can, which is a more familiar thing, that you can, there's a notion of Higgs branch, and it's known that the Higgs branch doesn't change by this S1 reduction. And then if you use 3D mirror symmetry, you can identify this with a Coulomb branch of the mirror theory. So in this sense, this vertex operator algebra can be also considered as a chiralization or a fine quantization of these Coulomb branches. Another thing is that the Higgs branch itself is not a complete invariant for this theory. Because there are many for the theory whose Higgs branch are just ones. So in this sense, you can consider vertex operator algebra as a refinement of Higgs branch, if you believe that conjecture. And so there's a subtlety in this conjecture that the Higgs, so this RV is not, mostly not reduced while Higgs branch is a reduced variety. So the isomorphism is only true if you take a reduced variety of the associated variety. But this non-reducedness is actually a good thing in the following sense. So there's another conjecture of Ross theory. If you consider the associated variety as a scheme, let me call it associate scheme. So this is already complete invariant. So you should be able to, in other words, you should be able to recover everything from this finite dimensional scheme, a scheme of finite value. And in fact, associate each vertex or operator algebra has a canonical filtration, so you can consider corresponding associated gradient. It is a commutative algebra. So this should be isomorphic to the coordinate ring of arc space of this associated scheme. This is arc space. So in other words, the vertex operator algebra should be quantization of arc space of the associated scheme. Any questions so far?
Is that the conjecture of beam? It's not nearest.
He said this conjecture in his talk, but it's not written either.
Well, if a physicist doesn't try to conjecture, I think it's not a good sign.
But it's okay for a mathematician.
Okay. So let me try to explain what is associated variety. In our favorite example. So it is affine vertex algebras. So let G be simple. The algebra and let G have the corresponding smooth algebra. this has already appeared in Thomas' talk, but for each number, complex number, which is called level, you consider a vacuum representation of G hat, which is an induced representation from one-dimensional representation of this parabolic subalgebra. Here GT act as 0 and P act as this number. Then one sees that this has a natural structure of a vertex algebra, and it's called universal affine vertex algebra. So you can talk about the representation of any vertex algebra, and the category of representation. So the representation of this vertex algebra is the same as smooth G hat module of level K. In this sense, you can consider this as a version of enveloping algebra of a algebra in the sense of the representations. So anyway, and so we are more interested in actually the simple quotient of this universal affine vertex algebra. So let me go by LK, the unique simple graded quotient of this induced representation, and which inherits a vertex algebra structure. So you can talk about the associative variety of both one. So let V be K G or LKG. Then this its algebra and the vector space is just a quotient of V by this subspace. And then you find that there's a surjection from symmetric algebra of G to here, which send monomial of this form to element like this. And this is certainly surjective because you forget elements which has power greater than 2. And so you can, if you identify this as a polynomial function on G star, you find that this is actually a map of Poisson algebra. This as a kernel, a phi, then associative variety is just 0 locus of a kernel of this map, which is a G invariant and conic subvariety of G star. So the situation, the associative variety of this affine vertex algebra is quite similar to the associative variety of a primitive ideal of UG. But if you take V to be VKG, by the PBW theorem, you find that the phi is isomorphism. So there's no kernel, which means the associative variety of this universal one is the whole space G star. And so if a level is irrational, then this induced representation is already simple. So associated variety of this one is the whole space. So this is quite different from the case of associated variety of primitive ideas, where associated variety is some nilpotent oblique closure which is contained in nilpotent form. But there's other extreme case where associated variety is just a point. And this happens if and only if this module is integrable as a representation of G hat. So it integrates to the representation of a loop group. And this happens if and only if K is a non-negative integer. So in other words, this zero associated variety condition characterize integrability of affine Katsumuni algebra modules. So, yeah.
What's x tilde in this case? What is x tilde?
You can describe that it's some certain fat point. You want me to explain?
Well, not now.
Okay.
But somehow, for some values of, I imagine for something like k equals 0, it's going to be a...
That's a point, yes. That's a point, yes. Yes, and yeah, so it's not, so we can extend, so integrability is not really defined for general vertex operator algebra, but you can use this as zero associated variety condition to define integrability condition to vertex operator algebra, and it's called the least condition. So vertex operator algebra is called least if and only if associated variety is okay. And so this already appeared in the talk yesterday, and it's known that these vertex operator algebra have nice properties. Very nice properties. So, for example, if it's also rational, then the module category has a structure of modular tensor category as a group like 1. So you can get the invariant of 3 manifolds for free, and also you can, as a character, you get a modular function for free from these and rational vertex operators. But of course, it's very difficult to find new such examples. And this law is talk about such an example for double algebras, I think, with this. Yeah? Yeah, so he will explain more about this. But the point, so most theory of vertex operator algebra assume this least condition. But the point here is that the vertex operator algebra coming from for this theory is not least unless, if you believe the conjecture of Beam-Rastelli, unless the Higgs branch is a point. So you want somehow generalize this condition so that you can use for vertex operator coming from for itself. Now there's another fact. The Higgs branch for this theory, for the Higgs branch of 3D theory, is expected to be symplectic singularity. In the sense of Bourville, by a theorem Caradine. So this means that this has finitely. So this is a hyperkiller, console particular symplectic variety, and the Caradine theorem says it's not symplectic. So it makes sense to introduce the following notion, which we introduce with Kawasetsu. Sitting there. So we call a vertex operator algebra is quasi-this. If its associated variety has finitely many symplectic leaves. So as I explained, all vertex operator algebra coming from for this theory are supposed to be quasi.
That when, like the universal one doesn't.
Is not quasi. It's only simple quasi. And so what we can show for quasi-this vertex operator algebra is the following. So in general, quasi-this can have infinitely many representations, while this vertex algebra only has finitely many. The so-called ordinary representations. So let's assume it's quasi-this. So ordinary means that those representations whose character makes sense. It's a direct sum of finite dimensional weight spaces. So this number is finite. So if you only care about those representations whose character makes sense, they're only finitely many. And for each such module, the character converges to holomorphic function on upper half plane, where Q is considered to be equal to 2 pi tau, and these characters satisfy is a subspace of a solution differential equation called the modular linear differential equation. So this character satisfies a differential equation called modular linear differential equation. And modular linear differential equation are certain differential equations which modular form satisfy. So in particular, there's a so this solution space is closed under the natural action modular. So this theorem implies certain modularity of the character of quasi-this vertex algebra, and if it comes from, for this theory, the character should be the same as Schur index. So the theorem implies some certain modularity of Sugar index. And this is important in physics also, because you can recover another central charge called acentral charge from the corresponding vertex of the charge, which gives another evidence that the image is a completely invariant. And another remark is that this character, so this does not follow from the theorem, but this is often, I mean, maybe always, but I'm not sure, a quasi-modular. If it's not a modular, which means this belongs to a ring generated by E2, E4, E6 Eisenstein series. So if it's modular, it belongs to the ring generated by E1 and E6. But quasi-modular means you add E2. And another remark is that the theorem, so this was proved by Howley recently. The theorem holds for a supervertex algebra by replacing character by supercharacter. And this supercharacter again seems to be always quasi-modular. So let me explain some example. So this simple quotient, the nicest one are integrable ones, but the integral ones cannot come from for this theory because it's unitary. So you have to consider a more general representation, and so if you consider admissible representation, I don't think I have time to define, but then one can show that its associated variety is some nilpotent orbit closure. So this case behaves exactly the same as associated variety of primitive varieties. And so this one, so admissible, so these come from for this theory, if it is so-called boundary admissible. So I will not explain more because Ken is going to talk about this case. I think so. She's talking about for the mirror symmetry. So these are examples of for this theory coming vertex of the coming from for this theory. And another interesting example is so-called class S theory. So this for the theory which is parameterized by some semi-simple group. and a punctured Riemann surface. I gave a talk on this several times. I will not explain in details today. But what I want to say for this case is corresponding vertex operator algebra was constructed by myself. Vigorously for genus 0 Riemann surface. And it was shown that the associated variety or Higgs branch are so-called more Tachikawa varieties. And this is for type A. You can identify with Coulomb branch of clear gauge theory associated with star-shaped field of this form, with a number of leaks, a number of punctures. Character of this vertex operator algebra can be computed, and it was shown by Miras that this coincides with up to eta function factor generalized multiple Q zeta value. So this is a certain family of vertex operator algebra whose character are quite interesting and whose representation theory is yet to be investigated. Now, I'd like to go to the topic of today. So, what I want to talk today is a conjecture of Bonetti any questions so far? Because there are many, so the for this theory is very rich, so there are many for this theory. So there should be many quasi-least vertex operators, operator algebras. And but the conjecture is the following. So for any complex reflection group which is generated by reflections in some on some vector space which I denote by V gamma, there exists a vertex superalgebra which I denote by V gamma, such the following holds. So first, its associative variety is isomorphic to the orthofold of tangent space of this ring gamma by the action of gamma, which is it is a symplectic singularity. So this is so the associated variety is a symplectic singularity naturally attached to this gamma, defined like this. So this in particular means that this vertex superalgebra is quasi-easy. And the second condition is that this vertex superalgebra has n equals to 2 symmetry, supersymmetry, which means it's an extension of n equals to 2 superconformal algebra. And in fact, it has n equals 4 supersymmetry if gamma is a Coxeter group. And the central charge of this vertex superalgebra is expressed in terms of a fundamental invariant of this Coxeter group by this formula, where this is a fundamental invariant, degree of fundamental invariance. So degree of fundamental invariance of this invariant ring, which is known to be a polynomial. And also, and Thomas yesterday said the free field realization is important for vertex operator algebra. The third condition is that this has a free field realization. So which means that V gamma embeds into a free field, which is beta gamma BC system. This generates wild vertex algebra. This generates Clifford vertex algebra. Tensor with rank 1. So for each complex reflection group, there should be a vertex superalgebra satisfying these nice properties. That's a conjecture. And a theorem is cannot prove this conjecture in general, but the statement that this conjecture is true for a symmetric group. And so how we prove is that we prove by constructing a sheaf.
Is it important what V is?
What V? Which V?
V gamma.
V gamma?
So do you just take reflection representation, meaning that there are no invariant vectors?
You take natural ones.
Well, I mean, which one is natural? Is it of dimension n of dimension n minus 1?
So this case is not important. Yeah. So let's take dimension n, and statement will be easier. Then the vertex superalgebra is can be realized as global section of certain sheaf of vertex superalgebra. Sheaf of vertex superalgebra, which is locally isomorphic to the beta gamma BC system of rank R of n.
Do you really want to have simplicity of that form? I mean, this includes some of the ADE simple singularity, but
Yeah.
you want to include it.
If it's outside of type A, then it's got complex.
Yeah, well, otherwise this reasonable version, whether you still have a replacement for the resolution singularity and many things here, but in slightly more general context.
Don't ask me that. It's a conjecture. So I'll explain what correspond. So let me make some remark.
What is Fn?
Hmm?
The sheaf, what is Fn?
It's a sheaf of vertex superalgebra.
Yes.
I'll explain a little bit more, but it's locally isomorphic to beta gamma BC system. So it's the beta gamma is a wide algebra. It's kind of a chiral version of a D module. But also put the fermions. So let me explain a little bit more about this sheaf. So, as everyone knows, Hilbert scheme can be identified with a Nakajima quiver variety associated with a Jordan quiver. So in other words, this can be obtained by certain Hamiltonian reduction. So that's how we construct a sheaf of vertex algebra. But if you do it naively, it doesn't work. Due to some obstruction in constructing sheaf of vertex algebra. And what we do is you replace this Jordan quiver by this kind of quiver. So this is a superspace framing. We change framing to by superspace of dimension 1, 1, and then you do the same, and then you get some super variety whose underlying topological space is the same as this one, and then you do a chiralization of this super variety. Chiralization means locally you replace wide algebra by system and fold algebra by BC system, and then you get a certain sheaf.
What is the super dimension of this super variety?
What do you mean by super dimension?
And what the other part?
It has the same dimension as the even part.
Okay, a 2n, 2n.
And then you get some sheaf well defined on this Hilbert scheme. But if if you don't do super, if you don't supernize, it doesn't work. To do some obstruction. The point here is really you need to consider super variety.
Obstruction to what? Which
To
sort of
construct C for vertex algebra. It does not glue. You cannot do Hamiltonian. So Hamiltonian reduction is replaced by BRST reduction. For the but this BRST reduction does not. You cannot define BRST reduction for arbitrary level. So you need to have appropriate level to do BRST reduction. But if you do non-supersetting, it does not satisfy this condition. But if you add super things, you get the correct level.
Is it some super cotangent bundle to some usual variety or not?
It's a chiarization of. So this super variety is structure sheaf of Hilbert scheme. And also the super part is the parity change of tautological band.
Percentage of what?
Tautological band. Corresponding to this node.
So somehow you need to deal with Hilbert scheme for the reason that the action is free on the stable part.
Right, yeah.
Just quantize, like C2n mod Sn, then it doesn't matter whether you do it on the fifth level and then take global section, so you just do reduction on the classical level.
Yeah.
It's also the case here.
Yes. So in particular, you can compute character of this vertex operator. And so, for example, for n equals to 2, Hilbert scheme is essentially a cotangent bundle to P1. And the sheaf on here, so this is essentially the so-called chiral drum twisted chiral drum complex on P1. And twisting comes from tautological band. So this sheaf is kind of generalization of twisted chiral drum, but because Hilbert scheme is not cotangent to something, you cannot really. And so in this case, this global section is product of n equals 2, n equals small n equals to 4 superconformal algebra. At central charge equals to minus times some free field called super symplectic Fermi. So so this one is the double algebra for simple quotient of S. Minimal double algebra of S. So in this sense, this vertex algebra can be considered as a generalization of this minimal double algebra.
SL22, right?
So A11.
The first symbol looks somewhere between 2 and 1.
And finally, one nice thing about the constructing vertex algebra from SIF is that the free field realization, you get free field realization for free. Can be obtained by as the so because you can consider the sheaf a restriction to a certain open set. And this gives a vertex algebra homomorphism. And if you choose appropriate open set,
So would that be like C to M?
yeah. Then you get the desired free field realization. Finally, this V gamma appeared in conjecture in general is vertex algebra associated with super Yang-Mills theory. So for while group is vertex operator algebra corresponding to 4-dimensional super Yang-Mills theory whose Lie algebra is G. This is a physical expectation.
G here. G. G no.
No, the other.
No, this is G, TG. So when gamma is a Coxeter while group, then it's expected that this vertex operator algebra is the vertex operator coming from super Yang-Mills theory. So what we constructed here is a vertex operator algebra for type A super Yang-Mills theory. Okay, I stop.